Hello and welcome to the second half of Chapter 7. We're going to start by taking a look at some more complex equations to solve, and then move on from there to some exponential rules. So we'll start with negative 3 times y minus 4 is equal to 36. Now to solve this, we can first simplify this left side of the equation by multiplying, right, or distributing this negative 3 into the parentheses. So we take negative 3 times y, we get a negative 3y. Negative 3 times negative 4, we get a positive 12, and that's equal to 36. Now we solve this using our addition and multiplication properties we learned last time. Subtract your 12 from both sides. We have negative 3y is equal to 24. Divide by negative 3. And y is equal to a negative 8. We can check this solution. We can plug negative 8 back into y into the original equation. Here we'd have negative 8 minus 4, which would give us a negative 12. And then negative 12 times negative 3 would give us a positive 36. So indeed that is the solution to our equation. Let's try one more like that. Let's do 5x minus 2x minus 3, and that will equal 27. Now here we're going to distribute this negative sign in front of the parentheses. We can basically treat that like a negative 1 being multiplied into the parentheses. Our 5x stays out front, and we have a negative 2x plus 3 is equal to 27. Now we can add our like terms, or subtract in this case. 5x minus 2x gives us 3x plus 3 is equal to 27. Subtract 3 from both sides. We have 3x is equal to 24. Divide by 3, and we have x is equal to 8. So again, we would plug this 8 back into both x's in the original equation if we wanted to check that solution. I'll leave that to you to check it. One other thing we can encounter is having a variable on either side of the equation. For example, 3x minus 4 equal to 8 minus x. Here we have an x on both sides of the equation. The first thing we want to do in this situation is get our variables all on one side of the equation. So in order to do that, we can use our addition property. We could add x to both sides of the equation. Right, what that does is cancels out the x on this side on the right and leaves us only with x variables on the left side. This gives us 4x minus 4 is equal to 8. Then we can solve it normally just by adding 4 to both sides. We have 4x equals 12. Divide by 4. And we have x is equal to 3 as our solution. Again, to check that, we would plug 3 back into both x's in that original equation and make sure that both sides give us the same thing. We can also apply these same ideas to formulas. For example, if I have s is equal to r plus p all over 2, and I want to solve this equation for r, I can do that just with some manipulation of this formula without having to know what s, p, or r are equal to. Here all I need to do to solve for r is to get r by itself. So the first thing I'm going to do is get rid of this fraction. I can get rid of fractions in an equation by multiplying both sides of the equation by the common denominator, in this case 2. So if I multiply both sides by 2, here I have 2s, and on this side, right, the 2's will cancel out, leaving me just with r plus p. Now to solve for r, I just need to get rid of this p, so I can subtract p from both sides. Now these are not like terms, so I'll write this out 2s minus p, and that is equal to r. and that is my final answer. I have r by itself and everything else on the other side of the equal sign. Let's try one more example of this. Let's take s is equal to w over 2 times a plus t. And this time we're going to solve for t. So here we have two choices. We can either distribute this w over 2 into the parentheses, which is what we've normally done, or we can multiply both sides by the reciprocal of this fraction to get rid of it from this side of the equation. If I multiply by 2 over w, and I do that to both sides, right here the 2 and the w's will cancel out, and I'm left with 2s over w is equal to a plus t. Now again, to get t by itself, I can subtract a from both sides. These are not like terms on the left here, so I have 2s over w minus a is equal to t, and that is my final answer. Next, we're going to take a look at some word problems. We'll start with this example here, just practicing writing this expression as an algebraic expression. So to do that, we just take a look at the information here. 8 inches less than twice the height. So twice some height, we don't know what that height is, we can call that height h. Right? Twice that height is 2 times the height, and 8 inches less than that would be subtracting 8 from that. So this here, 2h minus 8, is the algebraic expression for 8 inches less than twice the height. The idea here is just to take notice of those key phrases like less than, meaning subtraction, twice, meaning multiply by 2, and then taking note of our variables and our unknowns. If we change this phrase just a little bit though, for example saying 8 inches less twice the height, this is a different expression than saying less than. 8 inches less twice the height is saying 8 minus 2 times the height. So the main thing to note here is the difference between less and less than. That will be the most complicated thing we'll take a look at as far as expressions go. Most of the time it will be pretty straightforward. For example, sum will mean add, product will mean multiply, difference will mean subtract. Here, less and less than, those will be the important ones to remember this distinction between less and less than. Next, let's try our hand with this. The electrical resistance of a length of wire is equal to the resistivity of the metal times the length of the wire divided by the square of the wire diameter. Now we want to write this as an algebraic expression or equation. First thing we need to do is identify some of our values and variables. Here we have resistance. Okay, resistance we can call R. Here we have the length of the wire. Let's call the length of the wire L. Okay, here the resistivity. Okay, we can call that little r. And then we have the square of the wire diameter. So the wire diameter we can call D. Now let's go ahead and use those variables to go ahead and put this into an algebraic expression or equation. We have the electrical resistance of a length of wire is equal to, so the resistance of the wire is equal to, we can say then R is equal to the resistivity, which is our little r, times the length of the wire. So we're multiplying this by the length of the wire, which we called L, and that's divided by, so this is divided by the square of the wire diameter. So the wire diameter is D, and if we want to square the wire diameter, we square it like so. Okay, so this then is our formula from this sentence. Okay, just go ahead and make sure you read that over carefully and are certain that this indeed is the correct formula for that sentence. Now let's go ahead and use these skills to solve this problem. Family prepares a budget that allows for $220 per month to be spent on gas. Suppose gas costs $2.50 per gallon and their vehicles have an average gas mileage of 25 miles per gallon. The family wishes to determine the maximum number of miles, m, they can drive and stay within this budget. So we look through here, right? They refer to their budget and they tell us what that budget is. They talk about the cost of gas and tell us what that is, as well as the average gas mileage. They tell us what that is. The only thing we don't know is the maximum number of miles, m. They give us what they want us to use for our variable in this case. So let's see if we can't figure this out. If we want to know the number of miles that they can drive, we need to know how much gas they're using so that we can figure out with their gas mileage how many miles they can drive. So to figure out how many gallons of gas they can buy, we can take the price per gallon, so $2.50, right, times how many gallons they want, should be equal to, right, the total $220 per month that they're willing to spend on it. We can then calculate how much gas they can buy by dividing both sides of this equation by 250. And we have G is equal to 88 gallons. So they can purchase 88 gallons, right, and they can drive 25 miles for every gallon. So 25 miles per gallon times the number of gallons should equal the number of miles that they can drive. So we take 25 times 88 and we get 2,200 miles. So for that month, spending $220 on gas at a price of $2.50 per gallon, they can go 2,200 miles. Next, let's take a look at multiplying some expressions. Let's take 2x squared and multiply it by 3xy. Now let's break this down into its parts. Here 2x squared is really 2 times x times x. And this is being multiplied by 3 times x times y. Now we're multiplying everything here, so multiplication can be done in any order. 3 times 5 is the same thing as 5 times 3, so I can rearrange this so that it looks a little nicer. I'm going to group the things that are alike, so our numbers here, 2 times 3, and then our x's, so times x times x times x, and then our lonely y here. So now we can multiply these pieces together, simplifying this. 2 times 3 is 6. X times x times x is x to the third power. And y here is still just by itself. We have 6x cubed y. So that is the product of 2x squared times 3xy. Some things we can pick out of this is a rule of exponents. Whenever you have two things multiplied together, you can add their exponents. Here we had an x squared times an x, and we got x cubed. If we take x squared times x cubed, we add their exponents and get x to the fifth power. It's because there are 5 x's being multiplied by themselves here. So if we were to take a look at another example, if I took 4x cubed times 2x squared y squared, I can multiply my numbers together. 8 x cubed times x squared should give me x to the fifth, and then I still have my y squared here. If I divide, say, y to the fifth over y squared, I can break this down into its parts. Y times y times y times y times y. So 5 y's all over y times y, 2 y's. Now, here, these y's can cancel out. So they're a factor of the numerator and denominator. And we are left with 3y's up top, y times y, or y cubed. We can pull another rule of exponents out of this. When you are dividing things, you can subtract the powers to get your new power. So for example, x to the 7th y cubed over x to the 5th y squared. Okay, our x to the 7th over x to the 5th, we can subtract those powers to get our new power of x squared. And then y cubed over y squared gives us y to the 1st, or just y. And that is our simplified expression. This rule, however, can cause some problems. Say when I have x cubed over x to the 7th, my new power then is 3 minus 7, or a negative 4. We end up with a negative exponent. Let's take a look at what does a negative exponent mean. So if I look here, when I have 2 squared, this gives me 4. 2 to the 1st is just 2. 2 to the 0 is 1. Anything to the 0 power is 1. And if I continue this pattern, dividing by 2 each time, 2 to the negative 1st power then should be 1 over 2. 2 to the negative 2nd power then should be 1 over 4. What we can see from this is a negative power, right? 2 to the negative 1st power is the same as 1 over 2 to the 1st power. 2 to the negative 2nd power is the same as 1 over 2 to the 2nd power. So if we want to, we can rewrite something with a negative power with a positive power by flipping it, by moving it into the denominator. So here x to the negative 4th power is the same as 1 over x to the 4th power. So then let's use this to simplify. 5x to the 4th y squared over 15 x y to the 7th. We take this one piece at a time. We have 5 over 15. 5 over 15 reduces to 1/3, so 1 over 3. X to the 4th over x. Again, we can subtract our powers to get a new power, giving us x to the 3rd. And then y squared over y to the 7th, we can subtract those to get our new power, y to the negative 5th. This, however, we can rewrite, right? This 1 up here I don't need. 1 times x cubed is just x cubed. So I put my x cubed up top. And then I have my 3 down below still. My y to the negative 5th, I can make this a positive exponent by moving it down to the denominator. And when I do that, I now have a positive y to the 5th. Another way to look at this is when I have a larger power in the denominator than in the numerator, I can take y to the 7th, right? I can take that 7 minus 2, which gives me a new power of 5, and then I keep that in the denominator where my larger power was. That way I don't have to convert to a negative exponent and then to a positive exponent. Let's also try this with 12x to the 6th minus 9x cubed plus 6x all over 3x squared. Now, when I have something like this, each term in the numerator is being divided by the denominator. So I can simplify this, right, by focusing on each term one at a time. Right, my 12x to the 6th divided by 3x squared. I take 12 divided by 3, which gives me 4. X to the 6th over x squared gives me x to the 4th. Now, negative 9x cubed over 3x squared, negative 9 divided by 3 gives me a negative 3. X cubed over x squared gives me x. Now my 6x over 3x squared, 6 over 3 gives me positive 2. And x over x squared, right, my larger power is now in the denominator, so 2 minus 1 gives me a new power of 1, and I keep that x term in the denominator where I had that larger power. So this then is the simplified form of this division problem. We can use these rules of exponents to work with scientific notation. First, let's take a look at how to write in scientific notation. Scientific notation takes a big number like 3,600,000 and writes it in a shorter form. Okay, basically what we're doing is, rather than leaving our decimal here at the end, we want to write this number without having to write out all of these zeros. So we always move that decimal point just to the right of our first non-zero digit when going from left to right. Our first non-zero digit, 3, we want to put our decimal point there. So this would then give us 3.6, okay, and then we could drop off all of these zeros, but to maintain the idea that this is 3,600,000, we are going to multiply. Okay, this time scientific notation tends to use the x as the multiplication symbol rather than just the dot. So just a switch of symbols here. So 3.6 times 10, right, to the 6th power, because we moved our decimal place 6 places. So 3.6 times 10 to the 6th. 10 to the 6th is 1 million, so 3.6 times 1 million will give us back that 3,600,000. That's the idea behind scientific notation. So take larger numbers and write them in a shorter form, or to take smaller numbers and write them in a shorter form. Take a look at that in just a sec. Let's try a larger number one more time. So if I take 24 million, and I want to write this in scientific notation, instead of having the decimal at the end of the number, I move it just after my first non-zero digit. So I have 2.4 times 10 now to the 7th power, because I moved it 7 places. For really small numbers, such as 0.0000237, okay, I can rewrite this using scientific notation, again by moving the decimal place just to the right of our first non-zero digit. So just after the 2. This gives me 2.37 times now 10 to the, I moved my decimal place 1, 2, 3, 4, 5 places, but I moved it in the opposite direction this time. I'm going to multiply by 10 to the negative 5th. Okay. When I'm using small numbers here, right, 10 to the 5th would have given me, right, 2, right, 37000, right, or 237,000 if I had a positive 10 to the 5th. But using that negative 5th, right, that indicates a smaller number, right? 10 to the negative 5th is 0.00001. So the thing we need to keep straight, small numbers, I use a negative exponent, large numbers, positive exponent. So let's say I had 3.2 times 10 to the 7th power. To convert this back to regular notation, I would take my 3, my 2, and then I need to remember that that decimal place now goes to the right 7 places. So 1, 2, 3, 4, 5, 6, 7. And I fill in all these extra spaces with zeros. So I have 32 million from 3.2 times 10 to the 7th. Let's then do some operations with scientific notation. Let's take 2.6 times 10 to the 4th power, and we're going to multiply that by 3.5 times 10 to the 6th power. I just have 4 pieces here being multiplied, 2.6 times 10 to the 4th times 3.5 times 10 to the 6th. I can reorder this into its parts using that commutative property. 2.6 times 3.5 times 10 to the 4th times 10 to the 6th. 2.6 times 3.5 is 9.1, and we're multiplying that by now 10 to the 10th power, because when we're multiplying things with the same base, we can add their powers. The 4 plus 6 gives me a new power of 10. So 2.6 times 10 to the 4th times 3.5 times 10 to the 6th gives me 9.1 times 10 to the 10th. What about 4.5 times 10 to the 4th over 1.8 times 10 to the negative 3rd? Okay, in this case, again, I divide their pieces. 4.5 divided by 1.8 gives me 2.5. And then 10 to the 4th over 10 to the negative 3rd, again, using my rules for exponents here. 4 minus a negative 3 gives me my new power of 7. So I have 4.5 times 10 to the 4th divided by 1.8 times 10 to the negative 3rd gives me 2.5 times 10 to the 7th. What if I have 3 times 10 to the 5th multiplied by 4 times 10 to the 7th? Here my 3 times 4 gives me 12, and then I have times 10 to the 12th power. Unfortunately though, since my decimal is not just after my first non-zero digit here, I am no longer using scientific notation. This is not in the correct form for scientific notation. To fix that, I need to move the decimal from here over here. So I have 1.2 times now 10 to the 13th power. Because I shrunk this number, I needed to raise my power. Sometimes too, with division, I may end up with something like 0.8 times 10 to the 3rd. With this, again, my decimal is not after my first non-zero digit. It needs to be over here, so that I have 8 times 10 now to the 2nd power. My number got bigger from 0.8 to 8, so my power shrunk by 1, because I moved that decimal place 1 place. So that is how you will fix, right, your scientific notation when your decimal is in the wrong spot. Again, it always needs to be just after, just to the right of your first non-zero digit. That will do it for chapter 7. Be sure to look over the video again for any questions you have. Also bring your questions to class and we will go over them. Also, don't forget to print off and bring in your homework to work on in class, and I will see you next time.